Hill Air Force Base, Utah. A maintenance crew is working on an F-35. Routine inspection, standard procedure. Someone leaves a flashlight inside the engine intake. By the time they realize the mistake, it's too late. The engine starts up. The flashlight gets sucked in. In seconds, 43,000 pounds of thrust meets a $10 piece of equipment. The result? $14 million in damage. Your tax dollars gone. An engine that can't be repaired on site. And a viral story that exposed something the Pentagon doesn't want you to see. Because this wasn't about a flashlight. This was about a $14 million engine so complex, so fragile, and so expensive that the entire F-35 program is buckling under its weight. Today, we're exposing the truth behind the most expensive mistake in military aviation. And who's paying for it? You are. We need to go back before taxpayers spent $60 billion on an entire program, back before most advanced became code for most expensive, because what's happening right now didn't start with a flashlight in an engine. It started with promises nobody could keep, and decisions nobody wanted to question. Listen, I've spent 20 years watching defense programs. I've seen costs overrun, I've seen delays, but I've never seen anything like this. An engine that's threatening to ground our most advanced fighter. Not because it doesn't work, but because it barely works. And every time it fails, you're paying for it. You know the promotional specs, you've read the press releases. What you haven't seen is what's actually happening in the hangars. The data they buried, the warnings they ignored, the crisis they're managing quietly while your tax dollars keep flowing. This isn't about engineering. It's about what happens when the people spending your money never have to face the consequences of being wrong. But before we dive into the crisis, we need to understand what makes this engine so audacious and so fundamentally flawed from the very beginning. Because the F-35's problems didn't emerge from bad luck. They were built into the design from day one, and you've been paying for those mistakes ever since. Number 1. When 3 engines became one. The year is 1996. Inside the Pentagon, military planners are about to make a decision that will haunt American aviation for decades. They don't know it yet, but they're asking for something impossible. And here's what happened. The Air Force wanted a fighter that could take off from normal runways. Fast, agile, long range. The Navy wanted a carrier-based fighter. Reinforced landing gear, salt spray resistance, able to survive catapult launches that generate forces strong enough to break a normal airframe. The Marines wanted something else entirely. Vertical takeoff and landing, like a Harrier but better, much better. 3 different missions, 3 completely different aircraft, but Congress had a different idea. 1 aircraft, 1 engine, massive cost savings. On paper, it was brilliant. In reality, it was asking 1 engine to be a sports car, a dump truck, and a helicopter, all at the same time. You'd laugh at that idea, but that's exactly what the Pentagon demanded, and contractors lined up to promise they could deliver it. The numbers were insane. The STOVL variant, the Marines' vertical takeoff version, needed more than 40,000 pounds of thrust, but it had to weigh 20% less than any existing engine with that kind of power. It had to operate in salt spray, the Navy's requirement. It had to survive carrier catapult launches, 4 Gs of acceleration in under 2 seconds, and it had to redirect all thrust downward for vertical landing without melting the deck beneath. Temperature demands exceeded 3,000 degrees Fahrenheit, hotter than the melting point of most metals we knew how to work with. Nobody had figured out how to do this reliably, not at this scale. Picture this, it's 2001, Pentagon conference room. Pratt & Whitney's chief engineer is standing before a panel of military officials and congressional staff. They've just finished his presentation. The room is silent. Then the question comes, can 1 engine really do 3 missions? He pauses. He knows what his own team has been saying behind closed doors. The thermal management is borderline impossible. The weight requirements contradict the thrust requirements. The vertical landing mode creates stress patterns nobody has ever successfully managed in a production engine. The honest answer? Probably not. But GE is sitting in the waiting room outside, ready to give their pitch. And if Pratt & Whitney shows even a hint of doubt, they lose the contract. The entire company has bet on this. They've spent close to their entire annual R&D budget developing the proposal. So he looks the panel in the eye and says, absolutely, we can deliver everything you've asked for. In that moment, he commits the program to 2 decades of struggle. Now, understand something. Every defense contractor in that competition faced the same choice. Tell the truth and lose. All promise the impossible and fight it out later. The system doesn't reward honesty, it rewards optimism. And when the contracts are worth tens of billions of dollars, optimism becomes very expensive for taxpayers. Here's what the promotional materials won't tell you. The F-135 wasn't designed to be the best engine for any single mission. It was designed to be barely adequate for all 3. Think about that. the most expensive engine development program in history, and the goal wasn't excellence. The goal was just good enough. That compromise is written into every component, every specification, every failure mode we're about to discuss. When you try to make one thing do everything, you guarantee it does nothing exceptionally well. The Air Force got an engine heavier than they wanted. The Navy got an engine more complex than they needed. The Marines got an engine that works, but operates so close to its thermal limits that it's constantly on the edge of failure. This wasn't a design flaw. This was the design. And who's paying for this compromise? You are. Every taxpayer in America. Because when you demand one engine to do 3 missions, you don't save money. You spend it 3 times over. In maintenance, in repairs, in constant crisis management. The cost savings of jointness? It was a lie from day one, but admitting that would mean admitting the entire program was sold on false economics, so instead they just keep billing you. Pratt & Whitney won the contract in 2001. They promised an engine that would change everything. By 2006, the first production engines were running. By 2010, the problems were already appearing, faster than anyone expected. By 2015, the Pentagon had to completely revise their maintenance projections. The engines weren't lasting anywhere near as long as promised. Today, the program is managing, not solving, a crisis that traces directly back to that conference room in 2001. When someone promises you the impossible, they're not lying. They're just telling you what you want to hear and making you pay for it later. They won the contract, now they had to build it, and the design that emerged was nothing short of revolutionary. It incorporated technologies that had never been used at this scale, cooling systems that defied conventional wisdom, materials that were still experimental. On paper, it was brilliant, but brilliance on paper doesn't survive contact with reality. The engine they created had 28,000 parts, each one precision machined to tolerances smaller than a human hair, each one critical, each one a potential failure point. What they built was a mechanical marvel and a maintenance nightmare. Number 2. The mechanical marvel that became a maintenance nightmare. They built it. 28,000 individual parts, each one machined to tolerances smaller than a human hair, each one critical. And here's what nobody tells you. The more complex you make something, the more ways it can fail. The F-135 didn't just push complexity, it shattered every limit anyone thought possible. Let's talk about what makes this engine so different. It uses something called a 3-stream adaptive cycle architecture. That's engineer speak for, we tried something that's never worked at this scale before. Most jet engines are basically sophisticated blowtorches. Air comes in, fuel burns, hot gas shoots out the back. Simple, proven, reliable. The F-135 isn't simple. It has counter-rotating turbine stages. That means sections of the engine spinning in opposite directions at thousands of RPM. The tolerances? 0.0001 inches. That's 1/10,000th of an inch. A human hair is about 0.003 inches thick, so we're talking about precision 30 times finer than that. If anything shifts, thermal expansion, vibration, wear, those spinning sections can touch. When they touch at those speeds, the engine doesn't just fail, it explodes. Here's a way to understand this. Imagine building a Swiss watch, incredibly precise, hundreds of tiny parts working in perfect harmony. Now imagine that watch has to work while being hit with a hammer, repeatedly, while on fire, in a salt bath. Oh, and if it stops working, people die. That's what the F-135 has to do, every single flight. The complexity isn't there because engineers wanted to show off. It's there because those impossible requirements we talked about, the only way to meet them was to pile complexity on top of complexity, until the whole thing became so intricate that nobody fully understands how all the parts interact anymore. But here's where it gets really troubling. The thermal management system. Inside this engine, temperatures exceed 3,200 degrees Fahrenheit. That's hotter than melting steel, hotter than lava. How do you build something that survives that? Well, you don't. You cool it, constantly. With a system that's so complex it's almost alive. The turbine blades have cooling passages running through them, tiny channels that carry air to keep the metal from melting. How tiny? Smaller than a human hair. Hundreds of these passages in every blade, all of them critical. If a single passage gets blocked by debris, by carbon buildup, by a manufacturing defect, that blade heats up. And when it heats up, it fails. Fast. The failure cascades. One blade comes apart, the debris hits other blades. Within seconds, you go from a $14 million engine to a $14 million pile of scrap metal. Now, engineers knew this was a problem, so they developed ceramic matrix composites, new materials that can handle higher temperatures, revolutionary technology. Lighter than metal, stronger at high heat. On paper, it solved everything. In practice, it created new problems nobody anticipated. Ceramic doesn't fail like metal. Metal bends, metal cracks gradually. You can see it coming. Ceramic just shatters. No warning, no gradual degradation. And those cooling passages? Even harder to manufacture in ceramic, even easier to block, even more impossible to inspect. The solution to the heat problem became a reliability problem. Let me tell you what happened in 2018. An F-35B returns from a routine training mission. Normal flight, no issue reported. Post-flight inspection, everything looks good. 3 days later, different crew. Pre-flight checks before the next sortie. The crew chief notices something, a slight vibration during engine run-up. Barely perceptible, but he's experienced. He knows that vibration means something. They ground the aircraft, calling the engine specialists. What follows is 196 hours of disassembly. Over a week of round-the-clock work, they tear the engine down layer by layer, component by component, and they find it. A turbine blade, high-pressure section. It's been fracturing for months. The crack started in one of those hair-thin cooling passages, propagated slowly, invisibly. No inspection could have caught it. The crack was growing inside passages too small for any camera to see, too deep for any sensor to detect. By the time it caused that tiny vibration, the blade was minutes from complete failure. If it had failed in flight, the debris would have destroyed the engine instantly, possibly the aircraft. The engine is a total loss. $14 million gone. Here's the terrifying part. This wasn't a one-time event. It was the first time they caught it. How many other engines are flying right now with cracks growing in places nobody can see? Nobody knows. And here's what made headlines in 2024. Hill Air Force Base. Routine maintenance on an F-35A. A technician is using a flashlight to inspect the engine intake. Standard procedure. But when the crew closes up and prepares for an engine test, nobody does a final FOD check. FOD, Foreign Object Debris. The most basic maintenance protocol in aviation. The flashlight is still inside. Engine starts. The flashlight gets ingested. A 43,000 pounds of thrust. Within seconds, the turbine blades are destroyed. The compressor is damaged. Internal components shattered. Total engine loss, $14 million gone. Your money, not the contractors, not the politicians who approved it. Yours. And here's what made this viral. They couldn't repair it on site. The engine had to be completely removed, sent to depot, rebuilt from scratch. Months of downtime, millions more in labor and logistics. A $10 flashlight created a $14 million disaster. But that's not the real story. The real story is why these engines are so vulnerable that basic maintenance errors become taxpayer nightmares. Why the complexity that was supposed to make us safer actually made the engine more fragile. Why you're paying $14 million per engine when other countries get comparable performance for a fraction of the cost. Now pause for a second. Think about what that means. We've built the most advanced fighter in American history, and we can't tell if the engine is safe without taking it completely apart. By the time you know there's a problem, it's already catastrophic. That's not a bug in the system. That's the system. The complexity that gives us that incredible performance, it comes with a price, and that price is uncertainty. Every single flight. The industry loves to celebrate the F-135's thrust-to-weight ratio. Best in class, revolutionary, game-changing. Here's what they don't mention in those press releases. Achieving that ratio required making the engine essentially uninspectable without complete disassembly. Think about that. The military is flying engines they cannot thoroughly examine without taking them apart. You can't borescope deep enough. You can't X-ray through the density. You can't ultrasound through the complexity. The only way to know if an engine is truly safe? Tear it down completely. Inspect every component individually. Then rebuild it. That takes 200+ hours per engine. How often can you do that? Not often enough. So instead we fly on faith and statistics and hope. That's not advanced engineering. That's Russian roulette with a $14 million bullet. And you're the one paying for the ammunition. The Pentagon's own reports confirm this. Borescope inspection points, the tiny little cameras that can snake into the engine, were designed for simpler engines. They can't reach the critical areas in the F-135. The architecture is too dense, too complex, so mechanics do what they can. They check what they can reach, and they miss what they can't. By the time damage becomes visible on the outside, internal degradation is already catastrophic. The engine isn't failing, it's failed. You just don't know it yet. But the design complexity was only the beginning, because engines don't fail in laboratories, they fail in service. And as these engines entered operational squadrons, a pattern emerged, a pattern that sent shockwaves through the Pentagon planning offices, a pattern that threatened to ground the entire F-35 fleet. The engines weren't just complex, they weren't just hard to inspect, they were wearing out, fast, faster than anyone predicted, faster than any modern fighter jet in history. And the reasons why reveal something deeply troubling about what happens when you push engineering past its breaking points. Number 3. When cutting edge becomes cutting corners. The engines are flying, the complexity is manageable, the inspections are, well, we're doing our best. But then the mechanics started noticing something that should have been impossible. The engines were wearing out. Not gradually, not predictably, catastrophically fast. Let's talk about what Pratt & Whitney promised. 8,000 hours. That was the service life guarantee. 8,000 hours before an engine would need major depot-level overhaul. For context, that's reasonable. Modern fighter jets typically deliver 6,000 to 10,000 hours. The F-15's engines, about 6,500 hours between major overhauls. F-16's, around 6,000. So 8,000 was ambitious but achievable, or so they said. Here's the reality. Many F-135s are hitting depot maintenance at 2,000 to 2,500 hours. That's not a slight miss. That's 68% shorter than promised. Some critical components are making it past 400 hours. 400 hours! Legacy 4th generation engines from the 1980s lasted longer than that. Now here's where this gets expensive. The Department of Defense just revised their projections. Total program maintenance cost over the F-35's lifetime? $1.2 trillion. Not billion, trillion, with a T. That's more than the GDP of most countries. We're not talking about buying engines, we're talking about constantly rebuilding them. The F-35 was supposed to be cheaper to operate than legacy fighters. Instead, it's becoming the most expensive aircraft in military history, not just to buy, to keep flying. And who's paying for that? You are. Think about buying a car. A dealer promises it will run for 200,000 miles before needing major work, but at 50,000 miles, the engine needs a complete rebuild. $15,000. At 100,000 miles, another rebuild. Would you buy that car? Of course not. But the military doesn't have a choice. They've already bought 450 of them, with plans for 2,500 more. Cancelling now would mean admitting a $1 trillion mistake. So instead, they keep rebuilding and revising projections and hoping something changes on your dime. Now let's talk about why this is happening. The thermal barrier coatings, remember those impossibly high temperatures? 3,200 degrees? The metal inside the engine can't survive that, not without protection. So engineers coat critical components with ceramic thermal barriers, layers of material that insulate the metal underneath. These coatings were supposed to last the life of the engine. They're not. They're spalling off. That means flaking away, peeling, failing, and it's happening far earlier than anyone predicted. Here's where it gets scandalous. Internal documents show that contractors knew about manufacturing process variations, knew that some coatings were being applied inconsistently, knew the quality control was, let's say, flexible. But they downplayed it, because fixing it would have delayed production, and delaying production would have triggered contract penalties. So they shipped engines they knew had problems, with your money, to protect their contracts. When a coating fails, the base metal underneath is suddenly exposed to temperatures it cannot survive. The metal heats up, distorts, cracks, fails. Repairing coating failure isn't a quick fix. You have to remove the entire engine, send it to a depot facility, strip it down completely, recoat every affected component, rebuild the engine, test it, reinstall it. That takes months and costs millions. Remember when they promised on-wing maintenance? Quick repairs without removing the engine? That promise died the first time a coating failed. But even if you could repair engines quickly, there's another problem. Parts, specifically getting them. The F-135 uses single-source components. That means one manufacturer, one facility, one production line. High-pressure turbine blades? Made at one facility in Connecticut. Bearing assemblies? Single supplier in Ohio. Coating application, specialized facility with 18 to 24-month backlog. When something breaks, you can't just order a replacement from multiple suppliers. You wait and wait and wait. Lead time for critical components, 18 to 24 months. Let that sink in. If an engine fails today, the replacement part might not be available until 2026. We need to talk about what happened at Hill Air Force Base in 2021. Hill is one of the main F-35 operational hubs, major training and deployment center. Spring of 2021, maintenance crews are tracking the fleet status. 18 F-35As are sitting idle, grounded, not flying. They're waiting for engine components, not exotic experimental parts, standard maintenance items, high-pressure turbine blades, seal assemblies, components that should be readily available. But Pratt & Whitney's backlog is so severe that some of these aircraft have been grounded over 7 months. 7 months! Pilots are losing flight currency. You can't maintain proficiency if you can't fly. Squadrons can't maintain readiness certifications. The Air Force has minimum flight hour requirements. These squadrons aren't meeting them. Then the base commander starts digging deeper. He discovers something infuriating. Some of the parts they need? They exist. They've been manufactured. But Pratt & Whitney is diverting them to production aircraft. New builds for other countries, because the company can't manufacture fast enough to support both new production and fleet maintenance. So operational Air Force squadrons, aircraft that should be combat ready, are being cannibalized to support aircraft that haven't even been delivered yet. That's when people started asking the uncomfortable question: did we build an engine we can't actually sustain? Not can't afford to sustain. Can't physically produce enough parts to keep it flying. Now, the program office will tell you things are improving. Fleet readiness is up, they say. Engine availability is increasing. The statistics look better. Want to know why? They changed the definition. This is important, pay attention. Mission capable used to mean an aircraft could perform its full mission profile at full capability. Now, it means the aircraft can technically fly. Degraded engine performance? Still mission capable. Can't operate at full power? Still mission capable. Limited to certain flight regimes because the engine can't handle full stress? Still mission capable. Aircraft that would have been grounded under previous standards are now counted as ready. Because the degraded engine can still technically fly, just not at full performance, and not for long. The numbers look better on paper, but operational capability is declining. Think about that. We're counting aircraft as ready that can't actually perform their designed mission. That's not progress. That's creative accounting with national security. It's like saying your car is fully operational because it starts. Never mind that it can only go 40 miles per hour and the engine might seize at any moment. And when you ask who's responsible, who gets fired when a $14 million engine fails? Who loses their job when readiness rates drop below 50%? The answer is nobody. The contractors get paid regardless. Cost plus contracts guarantee profit. The program managers get promoted to their next major acquisition. The politicians blame the previous administration. But your tax dollars? Those keep flowing. $1.2 trillion in lifetime maintenance costs, and counting. Every engine failure, every coating repair, every supply chain delay, you're paying for all of it. And nobody, not the contractors, not the Pentagon, not Congress, faces any consequences for this mess. Want some context? The Eurojet XA100 powers the Typhoon fighter, costs about $4 million per engine. The Russian AL-41F powers the Su-57, roughly $3 to $5 million. Even the F-22 engines, also built by Pratt & Whitney, cost around $10 million each. The F-135? $14 million per engine, and that's the purchase price. Before maintenance, before the depot overhauls every 2,500 hours, before the coating repairs, before the supply chain delays. So what are you paying extra for? Complexity that breaks, integration that fails, stealth requirements that made the engine uninspectable, and fragility that turns flashlights into multi-million-dollar disasters. Other countries are flying capable fighters for half the cost per engine, but you're funding the most expensive engine in history. And when it fails, and it fails often, you pay for that too. Here are the real numbers. Flight readiness rates for the F-35? Consistently below 50%. That means less than half the fleet is truly ready to fly combat missions at any given time. For a frontline fighter, that's unacceptable. The F-15E Strike Eagle maintains 70 to 75% readiness. The F-16? Similar numbers. These are aircraft designed in the 1970s and 80s, and they're more reliable than our newest, most advanced fighter, because complexity doesn't equal capability when you can't keep it flying. So how do we get here? How did the most expensive engine development program in history deliver something that struggles to meet the standards set by engines designed 30 years ago? The answer isn't what you think. It's not bad engineering. Pratt & Whitney is some of the best engineers in the world. It's not manufacturing incompetence. These facilities have built thousands of successful engines. It's something deeper, something more fundamental. The answer lies in a decision made long before the first F-135 ever ran. A decision about what this engine needed to be. Not for the aircraft, but for the program. Because the F-135 wasn't just designed to power a fighter, it was designed to win a political battle. And when you optimize for politics instead of performance, you get an engine that looks perfect on paper, but struggles to survive reality. The truth about what went wrong? It's not in engineering reports. It's in the meeting rooms where promises were made that nobody could keep. Number 4. When the growth engine stopped growing. Here's something the program office doesn't want to talk about. The future. Not the distant future, the next 5 years. Because the F-35 has a problem that can't be fixed with software updates or new sensors. The engine has hit a wall. Let's go back to those early presentations, 2001, 2002. Pratt & Whitney didn't just promise an engine for today's threats. They promised an engine that could grow, adapt, scale. Future-proof was the word they loved to use. As the aircraft evolved, the engine would evolve with it. New weapons? No problems. More powerful sensors? We've got headroom. Advanced mission systems? The engine can handle it. The military loved this because threats don't stand still. An aircraft designed in 2000 needs to fight threats from 2040, so they built in growth capacity. Or so they were told. Here's the reality. The F-135's core design is so optimized for the original requirements that significant improvements require a complete redesign. Not modifications, not upgrades. A new engine. This isn't theoretical, it's happening right now. Block 4 upgrades, that's the current modernization program. New weapons, more advanced radar, better electronic warfare systems. Those upgrades require 20 to 30% more electrical power. Guess where that power comes from? The engine. The engine's generator is already running at maximum capacity. There's no headroom, no margin, no growth left. And it's not just electrical power. Every new system generates heat. Heat that has to be managed, dissipated. The thermal management system is already struggling with current loads. Adding 20 to 30% more heat, it can't handle it. The system is maxed out. Now here's where this gets interesting and frustrating. There is a solution. It exists. It's been tested. General Electric, remember them? They lost the original engine competition, but they didn't give up. They kept developing their design, improved it, made it truly adaptive. The XA100, that's what they call it. It delivers 10% more thrust, 25% better fuel efficiency, more electrical power generation, better thermal management. Everything the F-135 struggles with, the XA100 handles easily. The military tested it, flew it in an actual F-35. It works, so problem solved, right? Just switch engines. Here's why that won't happen. 2022, classified congressional testimony. A test pilot is answering questions about the engine comparison program. He's flown the F-35 with both engines, the F-135 and the experimental XA100. A congressman asks him directly, is there a performance difference? The pilot's answer is remarkable and damning. It's a different aircraft. The performance margin, the efficiency, the cooling capacity, everything the F-135 struggles with, this engine handles easily. The room goes quiet. Then another question, the obvious one. Why aren't we switching? The program manager stands up. His answer is bureaucratic perfection. Integration timelines and fiscal obligations preclude engine architecture modifications at this juncture. Let me translate that for you. We're stuck with what we have because admitting we chose wrong would cost someone their career and several congressmen their seats. Think about that. We have a better engine. It exists, it's been proven, but we can't use it. Not because it doesn't work, because admitting the F-135 was the wrong choice would be politically catastrophic. Here's what's really happening. The F-135 is built in Connecticut, Pratt & Whitney's home state. Thousands of jobs, billions in contracts. Connecticut's congressional delegation will fight any engine change. Then there are sunk costs. We've spent $60 billion developing and producing the F-135. Your $60 billion. Switching now means writing off that investment. No politician wants to authorize that, nor with their name on it. And Pratt & Whitney? They've designed the supply chain so that the F-135 production touches congressional districts across the country. Connecticut, Ohio, Arizona, Georgia, Florida. Each one has a congressman who needs those jobs in his district. The engine isn't just a technical program, it's a political protection racket. Your tax dollars funding a political protection racket, not a defense program, a jobs program. Each congressional district gets just enough economic benefit that their representative will fight any change. The weapon system becomes secondary to the economic system. And when you ask why we can't switch to the better GE engine, the answer isn't because it doesn't work. The answer is because it would cost jobs in the wrong districts. National security takes a backseat to political survival, and you keep paying for both, the inadequate engine and the political protection scheme keeping it alive. This is how programs become too big to fail, not because they work, but because cancelling them creates more political damage than continuing them. The F-135 will keep being produced, keep being installed, not because it's the best engine for the mission, but because it's the best engine for congressional district employment numbers. The defense industry loves to market the F-35 as software upgradable and future-proof. Every press release emphasizes adaptability, growth potential, evolving capabilities. Here's the truth they can't hide. The engine is the hard limit. Every planned upgrade is running into the same wall. New air-to-air missiles that require more power for cooling can't support them. Advanced electronic warfare systems, not enough electrical generation. Directed energy weapons for future threats. The thermal management can't handle it. We built a 5th generation fighter around a 4.5 generation power plant. And now we're watching the entire program's future dim, not because the airframe can't evolve, not because the software can't adapt, but because the engine can't grow. And no one wants to admit that fundamental mistake. So instead we get solutions, band-aids, workarounds, compromises, run the new systems at reduced power, accept degraded performance, lower the requirements, make the aircraft less capable so the engine can keep up. That's not future-proof, that's engineering in reverse, and you're paying for it. Pentagon planning documents confirm this. Internal memos describe the Block 4 power crisis as the limiting factor for capability growth. Not budget, not technology, not integration complexity. The engine. Some proposed weapon systems have been cancelled. Not because they don't work, because the F-35's engines can't support them. We're designing our military capability around the limitations of an engine we know is inadequate. Let that sink in. The threats aren't adapting to our capabilities. We're limiting our capabilities to match our engine. Which brings us to where we are today, and the question everyone in the defense community is asking but few are willing to answer publicly. How do we fix this? Not can we fix this, we know how. The GE engine proves it. The question is, will we fix this? Will someone in a position of authority have the courage to say, we made a mistake? Will Congress accept writing off sunk costs to avoid future disasters? Will the military prioritize operational capability over political convenience? Right now, the answer appears to be no, because the F-135 teaches us something uncomfortable about modern defense procurement. The technical problems are solvable. We have brilliant engineers, proven solutions, but the political problems? Those might be insurmountable. And when politics trumps engineering, everyone loses, except the people whose career depends on pretending everything is fine. The F-35 will keep flying. The F-135 will keep running. Each flight hour adding to the maintenance backlog, each sortie proving the limitations. Until one day, we'll face a threat the F-35 can't handle, not because the airframe isn't advanced enough, because the engine couldn't grow with it. And someone will ask, why didn't we fix this when we had the chance? The answer is already written, in congressional testimony, in political calculations, in the decision to protect careers instead of capabilities. Number 5. Lessons written in titanium and your tax dollars. We've talked about what went wrong. Now let's talk about who's paying for it. Spoiler, it's you. And it's going to keep being you. Unless something changes, because this story isn't just about one engine. It's about how we build things, how we make decisions, how we fail, and whether we ever hold anyone accountable. Lesson 1. When you try to make one thing do everything, it does nothing exceptionally. The military wanted to save money. One aircraft, one engine, maximum commonality. On paper, it was brilliant economics. In reality, we created a weapon system that cost more to maintain than 3 specialized designs would have. Jointness was the buzzword, efficiency through integration. But engineering doesn't work like that. Every compromise you make to satisfy one requirement degrades performance somewhere else. The Air Force wanted speed and range, so we added weight for carrier operations. The Navy wanted durability, so we added complexity for vertical landing. The Marines wanted STOVL capability, so we pushed temperatures beyond proven limits. Each service got 70% of what they needed, instead of 100% of what they wanted. That's not efficiency, that's expensive mediocrity. Here's the uncomfortable truth. If we'd built 3 different engines for 3 different aircraft, the total program cost would have been lower. Not higher, lower. Because specialized designs are simpler. Simpler means more reliable. More reliable means lower maintenance costs. The upfront development might have cost more, but we would have saved hundreds of billions in sustainment. Hundreds of billions of your tax dollars. We optimized for the wrong metric. We focused on acquisition cost and ignored lifecycle cost. The Pentagon celebrated a joint program that saved money on paper, but you're paying 3 times over in maintenance and repairs. Now we're paying the price. Every single day. And the people who made those decisions, they've moved on to other programs, other failures, but you're still here, still paying. Lesson 2. Latest doesn't mean best. The F-135 pushed technology to the bleeding edge. Ceramic matrix composites, exotic thermal barrier coatings, adaptive cycle architecture. Revolutionary, game-changing, never been done before. And that's the problem. New technology hasn't been tested by time, by millions of operational hours, by decades of real-world use. It comes with unknown failure modes. The ceramic composites were supposed to handle higher temperatures. They do, but they also shatter without warning. And they're harder to inspect and more expensive to replace. The coatings were supposed to last longer. They don't. And when they fail catastrophically. Sometimes the boring, proven solution is better than the revolutionary one. The F-15's engines uses older technology, less exotic materials, more conservative design. It's also more reliable, easier to maintain, cheaper to operate. Revolutionary sounds impressive, but reliable wins wars. There's a saying among old-school engineers. Anyone can build a bridge that stands. It takes an engineer to build a bridge that barely stands. It's meant as a joke, but there's truth in it. The F-135 is that bridge. It works, barely, expensively, temperamentally. It meets the requirements, but technically. But it operates so close to its limits that every flight hour is a gamble. Lesson 3. This wasn't just an engineering failure. Engineers knew these problems were likely. They wrote reports, raised concerns, highlighted risks. Procurement officials ignored them because acknowledging problems meant delays, and delays meant congressional scrutiny. Contractors overpromised, not because they were incompetent, but because honesty meant losing contracts. The system rewards optimism and punishes realism. When a competitor promises the impossible, you either match their promise or lose the bid. So everyone promises the impossible and hopes they can figure it out later. Political pressure to succeed created an environment where bad news was suppressed. Program managers who raised concerns were sidelined. Reports were rewritten. Metrics were redefined. Not because of malice, but because of institutional incentives. The system values the appearance of success over actual success. And now we're locked in. Sunk costs are too massive. Political investments too deep. Admitting the F-135 was a mistake means admitting decades of failure. Careers built on this program, congressional districts dependent on it. No one wants to be the person who pulls that thread. So instead, we manage the crisis. We work around the limitations. We redefine success. We've invested so much that we can't afford to admit we were wrong. That's called the sunk cost fallacy. And it's costing us billions every year. The F-35 program will be defunded. People will point to its combat record, its advanced capabilities, its technological superiority. And those things are real. But here's the uncomfortable truth. The aircraft succeeds despite its engine, not because of it. Pilots work around its limitations. They manage power carefully. They avoid maneuvers that stress the engine. They plan for degraded performance. Maintainers perform miracles. They keep aircraft flying that should be grounded. They cannibalize parts from one engine to fix another. They work 16-hour days to meet readiness targets. And you? You fund an entire support system that costs more per year than some countries' entire defense budgets. That's not success, that's survival. There's a difference. Success means the system works as designed. Survival means brilliant people compensate for fundamental flaws every single day, on your dime. The F-35 survives because talented people won't let it fail. But that's not what you paid for. You paid for an engine that would work reliably, that would last 8,000 hours, that would be maintainable without complete disassembly. You got none of those things. What you got was a $60 billion development program, a $1.2 trillion maintenance burden, and a weapon system held together by dedicated people working around a fundamentally flawed design. That's not a success story. That's a cautionary tale about what happens when nobody who makes the promises has to keep them. The F-135 reminds us of something important. Engineering greatness isn't measured in peak performance numbers, not in thrust-to-weight ratios, not in temperature tolerances, not in brochure specifications. It's measured in reliability, in sustainability, in the honest alignment between promises and reality. On those metrics, the most expensive engine in history is also one of the most expensive lessons. We learned, or should have learned, that complexity has a cost, that revolutionary technology carries risk, that political optimization produces technical compromise, that you can't promise the impossible and expect reality to cooperate. The question isn't whether the F-135 is a good engine. Under the constraints it's faced, it might be the best anyone could have done. The question is whether we learned anything from building it. Will the next major program repeat these mistakes? Will we again demand one system to do everything? Will we again chase cutting-edge technology without understanding the risks? Will we again suppress bad news because it's politically inconvenient? Right now, the answer looks like yes, because the institutional incentives haven't changed. The system that produced the F-135 is still producing programs today. The F-135 story is still being written. Every flight hour adds data, every failure teaches lessons, and somewhere, engineers are already working on what's coming next, hopefully with the humility this engine struggle should have taught us, but probably not, because learning from failure requires admitting failure first, and in defense procurement, that's the one thing we still can't seem to do. Remember that test pilot's testimony? It's a different aircraft with a better engine, but we can't switch, not because it doesn't work, because admitting we were wrong would be politically catastrophic. So the F-135 keeps flying, and you keep paying $14 million per engine, $1.2 trillion in lifetime maintenance, for a weapon system that survives on brilliant people compensating for fundamental flaws. That's not what you paid for. If this deep dive into defense procurement's uncomfortable truths got you thinking, hit subscribe, because someone needs to ask, where does all that money actually go? The next trillion-dollar program is already in development. Maybe this time we'll learn from the past, but probably not.